Uh, Good afternoon, everybody. My name is Enrique Valera. Thank you very much for being here. I am a research assistant professor at the Department of Bioengineering at UIUC. And today, I will work about the work that I have done together with Professor Rashid Bashir in the development of platforms for the detection of SARS-CoV-2 virus and other respiratory viruses. All the platforms that we developed are meant to work at the point of care. So important features of these platforms are they need to be provided a rapid response to the user. We always work with isothermal amplification technologies, and of course they need to be portable. Right? So in these 4 years with the pandemic, we have learned a lot of things about the disease. We have learned about a lot of things about the virus. And one thing that we learned is that the virus is unlikely to go away, right? So we expect the COVID-19 disease will become endemic, meaning that when we design platforms for detection of the virus, we cannot only think in a platform to detect the virus, right? We need to think a little bit farther, and maybe we need to add multiplexing capabilities to our devices. We need to give the option, for example, of detecting and distinguish multiple variants. And also we can distinguish and detect multiple viruses that are respiratory viruses and that can find in the same sample. For example, right now we are working in a device that can detect simultaneously from the same sample SARS-CoV-2, influenza A, influenza B, and also RSV. While the stay-at-home order was in effect in the state of Illinois, most of the people in our lab were listed as essential members of the university to conduct critical research on COVID. Right? So these first month of the pandemic were crazy for us, and a little bit stressful as well. We work 7 days a week, 10 hours a day. But with this, in March 2020, we received approval for the first IBC to conduct COVID-19 research in our campus. Also, a couple of months later, we received approval for 2 IRE protocols, one with Carr Hospital and the other one with OSF Healthcare in Peoria, to gain access to SARS-CoV-2 clinical samples, saliva and VTM. And actually, the saliva samples from Carl were used to develop the COVID shield test. I participated in writing this IRB. Professor Bashir was co-PI in this protocol. And together with all these efforts, we were like among the first to report a point-of-care device for the detection of this virus. As I said before, all our devices meant to work at the point of care. So it's important that we provide a definition of what is our vision of a point of care, right? So, of course, point of care approaches are those that can provide results at the point of use. Point of use could be a home, hospital, urgent care centers, elderly care centers, or emergency rooms, right? Important requirements is portability. We need a device that is decentralized, meaning that doesn't rely in a centralized lab, meaning that doesn't need a specific personnel that have been trained for the use of the assay. This device needs to provide rapid response to the user and needs to be sensitive in comparison with the gold standard techniques, right? But hopefully at a cheaper cost. As you can see here in this picture, as we increase portability, we reduce the size of the device, but also we reduce the number of tests that we can perform per hour, right? For example, if we have a handheld device, maybe we can test 3 tests per hour. On the other hand, if we have a centralized lab or if we have a trailer, we know from the COVID shield test that we can perform thousands of tests per day, right? But these are the extremes. There are like middle points, right? And that also enter in our definition of point of care. So for example, we can have a suitcase or a benchtop that is portable and can be used to test a small gathering of people, like this symposium or a concert or a sport event. So in the beginning of the pandemic, everyone learned about like these 3 main type of tests, right? The molecular diagnostics, the antigen tests, and also the serological tests. One important question that we ask ourselves is, okay, we will focus in molecular tests. What are the targets that we want to detect, right? From the RNA sequence, we focus in in the S gene and in the N gene. Another important question that we ask to ourselves is, what is the specimen that we will detect, right? So the gold standard at the beginning was the use of the nasopharyngeal swab. Right now, I think the clinic is moving more to the use of nasal swab, but many people, including us, consider the use of saliva as a possible specimen as well. For sure, easier to collect and didn't require like a specific swab or a specific receptacle for collection. That was very important, especially in the beginning of the pandemic. So, as I said before, we focus in isothermal amplification technologies. The gold standard for amplification of DNA and RNA is PCR. PCR is great, is very robust, very reliable, and very sensitive, right? But provide results in about 90 minutes. And the instrumentation needed for PCR is a little bit bulky because you need these very quick and precise change in temperatures. On the other hand, we have the isothermal amplification technologies, which LAMP probably is the most well-known at this point. There are some commercial devices already that use LAMP. And the instrumentation that you need for LAMP is smaller because you only need to apply a constant temperature, right? Basically, you just need a heating device that can provide a constant temperature from 60 to 65 Celsius degrees. Sensitivity is similar to PCR, and in theory it could be more specific, but because we are using 4 to 6 primers instead of only 2. Also, the enzyme that LAMP uses is different. The PCR, we use the BST DNA polymerase, which is very robust enzyme and is known for being less sensitive, less susceptible to contaminants, which open the door to the elimination of the viral purification step. So the main features when we design and develop a device are, we work with RT-LAMP-based assays. We have been focused in the use of RT-LAMP for respiratory viruses. For other applications, we now start working with RPA as well. But for respiratory viruses, we have only worked with RT-LAMP so far. We try to avoid always the viral purification step. We design and develop 3D microfluidic devices for our cartridge. We always try to implement multiplexing capabilities to our devices. And also we have developed devices that can work with VTM, with saliva, but right now we're moving to just using a swab, right? We want to stick with the swab because it's something that is more direct compatible with clinic, but we want to use swab without the need of a VTM. Also, our reader is compatible with the use of smartphone, and we have implemented like a smartphone app that can help us to take the images that we need in a more automatic way and also do the real-time analysis. As the pandemic evolved, our technologies also evolved, right? So, and in these 3 years, we have like developed 3 generations of our technology. In the first generation, we detected just one target, and using this push action, using these 2 syringes here, one for sample, one for the reagents. In the second generation of the device, we added multiplexing capabilities, just testing 2 targets and replacing the push action with a pull action to infuse the solution in a reliable way to the cartridge. And in the generation 3, that is the one that we're working now, this one is not published yet, so we have developed a device that can detect 4 targets, as I mentioned before, SARS-CoV-2, influenza A, influenza B, and RSV, plus 2 controls, one positive and one negative. We have incorporated a suction pump in the cartridge. Also, we have developed a customized tube that is like the interface between the swab and the cartridge. And also, we don't need any liquid reagent inside the cartridge. Everything that we have inside the cartridge is lyophilized or dry. And with all these things combined, we have a device that doesn't need any pipetting or any syringe. All this work has been done thanks to great and very committed students. One of them is Jong-Won Lim, he was here with me today. I will explain more in detail the first generation of our device. As I said, we start with the collection of the swab. Then we just put the swab inside our customized tube. We stir a little bit the swab, and then inside the tube we have a lysine solution that helps us to break the virus and release the RNA. In the bottom of the tube, there is an aluminum foil, and in the cartridge, we have like a piercing element. So when you snap in the tube, the piercing element breaks the aluminum foil, giving access to the live sample to our cartridge. As I said, we also have this suction pump element that can help us to aspirate the solution from the tube to the cartridge. Let me see if I can repeat this video. Okay, so in this video you see the student that is inserting the tube and using then the pump to aspirate the solution. These white things here, those are the lyophilized reagents. There we have all the enzymes, the fluorophores, the buffer, everything we need. And you can use the pump to move the solution back and forth to very well reconstitute the solution. Then we have like a mixer region when we mix things very well, and then we split the solution in the 6 reservoirs that we use for detection. Then you can insert the cartridge in our reader, and inside the reader we have this heating element to provide the 65 Celsius degrees that we need for amplification. And using the smartphone, you can read amplification as a fluorescence event, as we can see in the other video. I will give more detail in the cartridge. So these are all the elements that we have right now. As I said, we have this. We have this pumping region, right, that has a screw action and also have an elastic pump that is also 3D printed. The original position of the pump is down, so when you open the screw action, you aspirate the air from the cartridge and also the light sample from the tube. We have this customized tube that has the aluminum foil that I mentioned in the beginning. We have this reconstitution region where we have all the lyophilized product for the assay. Then we have this 3D microfluidic mixer, where we mix everything, all the reagents with sample very well. And at the end, we have this detection region with this fan shape, right? So we split the sample in 6 for the 4 targets we want to detect and also for the controls. And in each detection region, we dry the primers previously to give a specificity to the device. We have done this work in collaboration with Professor Bill King from the MEXI department. Now, I will give a little more of detail in the cradle. So as I said, our reader is compatible with the use of a smartphone. The reader includes all the lens, filters, LEDs that we need to adapt the use of the smartphone to read the amplification assay. Also, we have included this magnetic clamping device to make sure that the cartridge doesn't move, it's very steady during the amplification event. And also, of course, we have the heating element to provide the temperature that we need during amplification. And we have done this work in collaboration with Professor Brian Cunningham from the ECE department. One very important piece in the validation of our devices is the use of clinical samples, right? And we are very grateful with the collaboration that we have with Carr Hospital and also with OSF Peoria to get access to these clinical samples that we use for the validation of our devices. For example, in the generation 1 of our device, we got access. We use our device to compare or to test 20 clinical VTM samples, and we demonstrate that our device was able to distinguish positive from negative in 30 minutes. Even though we detected only 1 target, we had this pie shape with multiple replicates, but this generation of the device only detected 1 target at that time. Then, in the second generation of our device, we found the variants, right? So we found that the virus was mutated, and in this work, we focus in a device that can detect and distinguish the UK variant from the earlier strains. We found this interesting characteristic in the UK variant, what is the S gene target failure. So meaning that in the early strains, the S gene is complete, and in the mutation, there is 6 bases that are not there. So we developed primers to focus to these 6 bases. So And we tested simultaneously the N gene and the S gene. In the case of the early strains, both detection regions amplify. In the case of the UK variant, only the NG region amplify. And we use this way to not only detect, but also distinguish, and also for, distinguish from negative. We always try to add as well good controls to our development and validation. Typically, we had the control from the hospitals in the case when we're using VTM samples, but in this case we work with saliva samples, and there was no control from PCR using saliva samples in the hospital. So we developed our own control with PCR in collaboration with Professor Leiwan, that is also here today. In the first generation of our device, right now we are working, as I said before, just in the detection of the virus directly from dry swab. There is no any VTM involved. And we have developed a new IRB with Carl where we have access to clinical samples that are dry swabs directed to us to validate our device. So we will start collection of these samples next week. But so far, we have demonstrated our device with spike samples. Okay, so as I said before, we have this fan shape with 6 regions. In each region, we identify one target at a time. So we have influenza A, influenza B, SARS-CoV-2, RSV, and the positive and the negative control. The positive control always amplify, right? So in this example, we have a sample that is only positive for SARS-CoV-2. So we have 2 reservoirs amplifying. In this second example, we have a sample that is positive for influenza A, SARS-CoV-2, and RSV. So these 3 reservoirs plus the positive control amplify, and this is a very easy way that we have to not only detect but also distinguish the presence of different viruses in the same sample. We not only focus in optical approaches during these 3 years, we also put some efforts in electrical approaches. And before the pandemic, we learned that if we develop crumple graphene-based FET transistors, we can increase a lot the sensitivity for the detection of DNA. Also, we learned that the graphene has this very interesting characteristic that single DNA can be absorbed on the surface of the graphene. However, double-strand DNA is not absorbed on the surface of the graphene. So we combine these two, and we develop a method to detect the positive samples after amplification. So for example, if there is no virus in the sample, you have your primers that are single strand, there is no amplification, and the primers are absorbed on the surface of the graphene, so you can see this shift in the electrical signal. However, when there is amplification, there is virus present in the sample, and you have amplification, you consume all the primers, everything turns to double-strand DNA, and there is no absorption on the surface of the graphene, and there is no shift in the electrical signal. So in this way, we found a very easy way to electrically distinguish positive from negative samples. And also, we validated this with a VTM clinical sample from OSF Peoria. So this is the list that all the papers that we have published in the SARS-CoV-2 domain in the last 3 years. Most of them are research papers. We have also published a perspective, a review paper, and we also collaborated in the Nature Communication paper from campus. This list is not complete. We expect to publish soon the first generation of our device. And now the question is, what is next, right? So we know that molecular diagnostic tests are the gold standard for detecting the presence of the virus, and this technology is very sensitive, very reliable. However, it's still taking longer than desired, right? On the other hand, so we know that using amplification techniques, we can lower this time like half, 2/3, but still longer than desired. On the other hand, we have the antigen tests, right? That they are very rapid and even can provide results in just 5 minutes. However, the sensitivity is not the same as the molecular amplification test. So the next step is develop molecular amplification tests but can provide results in the time of the antigen test. That kind of technology will replace completely the need of the antigen test but providing the sensitivity of the molecular test. So stay tuned, and we will continue working on that. And with that, I would like to thank our students, collaborators, and also funder companies, funder entities. And thank you very much for your kind attention.
So how much does it cost?
Well, and this is research. This is research, and research is very expensive. Okay, so I think this is something that is very important to understand, especially for the people that is coming out of research, right? So right now for us, just the fabrication of one cartridge is about $200. But we are not fabricating in mass production, right? So as soon as you escalate the fabrication of all the pieces, this can go down to less than $10 or even $5, right? So yeah, I think it's not fair comparing the cost of research what you can put in the market, because of course we don't have any mass production capabilities.
How big is it actually? You know, if I had one,
Right.
handed it to me, how big is it?
Okay, so the cartridge itself is like this size. So if you remember, I think the reference, the good reference is the smartphone, right? So this is the size of a smartphone. So this is the size of our cradle.
Okay, got it.
Please.
So currently the prototype is only one sample, correct, that you can run?
So yes, so this is a thing for a handheld device, right? For a single user at home, for example. And yes, we are running just one sample at a time, but testing 4 viruses simultaneously.
And it's 30 minutes for
It's for 30 minutes to distinguish positive from negative, but depending on the virus and the concentration, of course, we can have a positive response much earlier than that, even that 10, 15 minutes.
So it's supposed to be, end users should be, it can be used at home, it can be used by anybody, layman.
Right. So right now, with the use of nasal swabs, right? So everyone just can collect the sample by himself, right? I think we are doing right now with the antigen test at home, right? So you can use that swab directly that you collect yourself and put it directly in our customized tube and then cartridge. So the idea is that there is no the need of a trained personnel to run this.
So I have another question.
Mhm.
How soon to market?
Well, at the end, depend how soon a company wants to put this in the market, right? So we are academic institution, we're researchers. Our goal is to bring new knowledge, new innovations, but not to put something in the market at this point, right? So there are some collaboration with companies, but it's not something that I will do personally.
That was going to be my next question. Do you have any potential companies already looking into this kind of technology?
Right. So as I said, so one of our founders was a company. So yeah, they depend on the interest of to put this in the market.
Do you have any idea what they're thinking when it comes to getting on the market?
Well, they need to do, I think, like any other company, like a study of the market,
Yeah.
right? To see what is the real market, the potential market for a test like this. But I think that could be very, very useful to have a quick response or quick analysis of the samples, and especially for the user. At this point, there is no any, as far as I know, any device or technology that can be used at home for the analysis of multiple viruses, right?
Not that I know.
Yep. Please.
Is it patented, and also will you go through FDA?
So we patented like the original design of the cartridge. The primers that we design are publicly available in the papers that we have published. The amplification technology is commercial available, right? So what we patented in the beginning of the pandemic was the design of the cartridge, the original design.
And will you, at what point would you go through FDA?
Okay, so if you want to really go to FDA, so you need to have like a company or someone that wants to put this in the market, right? So, and then you need to have like a clear lab to do all the validation in under a control environment, I would say. Is not something that I'm planning to do right now.
The action of the pump, the head, is it basically, how does that work? Where does that pressure come
It's just a screw action. So in the original position with the, let me see. Oh, here, yes. So in the original position with the screw pieces down, right? So you are pushing down this bellow, right? So when you screw up and release the bellow, you aspirate the air from the cartridge and also the lice sample from the tube.
What are some of the advantages over like an antigen-based test?
Well, in general, as a concept, a molecular diagnostics test has the advantage of the sensitivity, right, over the antigen test. So we can say like 100 times more sensitive, especially when you want to detect the presence of the virus in the early stages, right? So this is the main advantage of the molecular diagnostic test as a concept. In this particular case, the additional knowledge or the additional advantage, innovation that we are in here is the capacity of detecting multiple viruses simultaneously from the same sample.
I know a bunch of people that would like to have that right now.
Yeah? So we have this in the lab right now. Thank you very much. Okay, please.
So the cartridge design can handle only one virus at a time or multiple viruses?
No. So can handle only one sample at a time, right? One sample, but viruses, so we can detect up to 4 plus the 2 controls, right? So this is like this example here,
Okay.
right? So for example, you have this sample that is positive for 3 viruses.
Okay.
You can see this and distinguish them simultaneously. And for other applications, for other viruses that are blood-borne viruses, right now we have increased to more viruses as well. So yeah. Okay, no more questions? Thank you very much for your attention.